Okay, so the summer school which I was attended was called, I think, first summer school on non-relativistic physics and quantum field theory, something like that. I didn't write it down, so sorry. It was organized by Nordita, and it was through Zoom. So you can find all the videos and slides on this address. There were 5 series of lectures, all were about some aspects of non-relativistic physics, and I choose for this seminar lecture given by Jan Rosseel, and the lecture was called Non-Lorentzian symmetries and their gauging. And the first half of the series I will present now. It's about it will be about gauging of algebras. First, I will gauge relativistic algebra, which will be Poincaré algebra, and we will get a Lorentzian geometry from this gauging, from this algebra. And in the second part, I will gauge non-relativistic algebra, Galilei algebra, and we will see what is different from the gauging of the one of the non-relativistic algebra. Just a short note, there is a bunch of non-relativistic algebras. There are a lot of procedures how you can get a non-relativistic algebra by, for example, algebra contraction, also by algebra extension. You can get a lot of non-relativistic algebras, but I choose just 2 or just 1 to show you today. So let's start with a relativistic one. So we will gauge a Poincaré algebra. So Poincaré algebra is a relativistic one, and it has 2 generators, PAs. There are space-time translations, and MAB, there are Lorentz transformations, and the commutation relations are these. So translations commute with each other. Yes?
So you say that in the number
yeah.
What about the
Ooh.
what you got till now? That's
I think yes. I don't know. I think there should be also a lot of relativistic algebras, but we know that the Poincaré should be the one.
yeah.
But in the non-relativistic case is more complicated because there is a lot of strange stuff. Yeah. Okay, the question was, so what is a definition of relativistic algebra?
guess it's just Poincaré, right? That's done.
Sorry? I think relativistic algebra is a class of algebras which. Yeah. Something like this, I think. It's, yeah. But, you know, Lorentz algebra, like it's Poincaré without. Don't know. I don't know. Yeah. But I think what Standa was told is you should have some signature or to say it. Yeah. There is Lorentzian signature.
If you find the Lorentz configuration, like if you do some commutations, isn't like one of these vectors related to the matrix?
Not commutators. Oh, okay. You mean something like this? That here is Minkowski metric, and when there is, let's say, just delta or another metric. Okay, but okay. Sorry.
The point of the manifold, all of these commutators are bounding in the same point. And A and B are exactly the same point X or X and Y.
Okay. The question is about where the these generators acts, and this happens in the tangent space of the manifold. So you choose a point on the manifold, and on this tangent space, these operators acts. So it's in the same point. Okay. Because these indices are tangent space indices. We will have space-time indices later. So P's are space-time translations, MM are Lorentz transformations. This tangent space indices goes from 0 to d minus 1. Dimension of the manifold is d, and M is antisymmetric in its indices. And now I will tell you what I mean by gauging. By gauging, I mean how to associate gauge fields to these generators. How from these gauge fields we can obtain from these gauge fields we can obtain some geometric quantities like curvatures and even covariant derivative and so. And by these quantities we will define geometry. Okay. So the gauging procedure will have 3 steps. In first step, we associate gauge fields to each of these generators. So associate gauge field. And gauge parameter. To every generator. So we have 2 generators, space-time translations and Lorentz transformations. And gauge field will be a field on the manifold with one space-time index and with the index structure of the generator. So for translations, spacetimes, it will be some gauge field E mu A. And for the rotations or Lorentz transformations, it will be omega mu AB. There can be anything, okay? A priori, we don't know what it is. And after the gauging, spoiler alert, these will be field binds and these will be spin connections. But a priori, we don't know what we will get from the algebra. Of course, the question was if they are completely arbitrary. No, there have some induced transformation rules given by the algebra. I will show you. Why the index structure? Loosely speaking, because I will need the contraction of the indices. One new. It's a form on the manifold. One form on the manifold. Yeah. Okay, and the parameter. Something. So zeta and sigma. Okay. I will comment of the parameters later. So this is easy step one. Just associate a gauge field and parameter to each generator. In step two, we will, from the algebra, we get transformations of these fields. And we can, and from again from the algebra we can get a field strength of the algebra, which will play a role of curvature in the geometry. Curvature. So step two. Write down gauge transformations and gauge covariant curvatures. And this can be done through the known formulas from the constant structures constant from the algebra, but there is a much easier way, and the easier way is to define Poincaré algebra valued quantities. First will be a Poincaré algebra valued one form, a mu, which will be defined as contraction of gauge field and its generator. And the parameter in the same way will be contraction of the parameters and generators. So zeta and sigma. And when we have this Poincaré algebra valued quantities, the transformation rule for both gauge fields can be written compactly like this. So it's, I think it's I think it's look like that the fields are in the adjoint representation, something like this. And from this, when we plug everything, we obtain the transformation rules for gauge fields. So the derivative of the parameter is from the first part and from the second part. We get this because in the bracket there will be once Here will be ones P and M and the opposite way. And because we are in the tangent space, this gauge field in the lower index, in lower tangent index, just mean interaction with eta. It's a metric on the tangent space. we don't have a metric on the space-time. We will get the metric in the space for the space-time later. So we can just lower and raise the tangent space indices. And the second gauge field transform as I hope I wrote it right. So it's antisymmetric in A and B here. So this is transformations with respect to the local transformations. So with respect to, this is the parameter for the space-time translations, and this is for Lorentz transformations. But what we will need in geometry, you don't really are interested in the local transformations. You are interested in diffeomorphisms with respect with all the transformations. So with rules of generality, we can change these local transformations for diffeomorphism. And we will see that this guy transforms like a tensor, but this one not. And this is done by a redefinition of the parameters. So let me just write that we want to swap local translations for diffels. Okay, loosely speaking, local transformations has a tangent space index. Diffeomorphisms will have a space-time index, just loosely speaking. And this swap is done with the this gauge field. So psi mu is the generator of the diffels. Just use this gauge field. It's true because this is field bind. We still don't know it. So the that is generate diffels. This means that when we change a space-time point, the change is by this vector. So it's generator of the diffels. And we need to change also sigma parameter. Psi plus another tangent space parameter. This is I understand it that something like just changing the basis of our problem. It's just a technical to get a better version of the geometry than okay, just to illustrate what we have done here, the old gauge transformation, old delta, for a new E mu A field, the transformation with respect to the fields will change like this. Okay. I will say what is R in a moment. Yes? No. Space-time, no. Why? I think all indices they are still not. You must wait. Oh. Yeah. It's vector field, and so I think not, because you can just think about it like dual space without a trick. Okay, but the important is that this is the Lie derivative. Lambda is the redefined sigma. It's another choice of parameter in Lorentz transformations. It just shift. It's a parameter in Lorentz transformations in another basis. Sorry. It's defined by this relation. Sigma we have before, psi is defined here, and lambda is something which is the rest of this. So I can write it in the different way, like this minus. It's new parameter. It's in tangent space. It's just a technical, because we swap local things for the fields, and the price for it that we must redefine also this. No, they are just in tangent space. Yeah, they are defined everywhere. It depends on space-time's point, but yeah, but it acts just on the tangent space. But okay, they are just translations. They are just shifting of coordinates, and the fields are more general. There is a more. It's I think about this like tailored.
So essentially, you are saying that you're restricting the type of local translations to the ones which are generated by people.
But all local transformations are defined by the fields, no?
Yes,
not yet, but it will be invertible.
So you're just changing the base.
Yeah, I'm changing the basis.
Yeah, but there's no restriction. It's just that you want the curve in there.
Yeah, and
But
it's
just as clear.
yes,
It's just
but differs are better in the way that you can easily found that something is a tensor and something is not a tensor.
sure.
So this is for this purpose to make it easier. It's just changing a basis. It should be written just with this plus. Okay, so why we did this was because now we can easily see what is a tensor. This is a tensor because this transform like tensor with respect to space-time indices, and with respect to tangent indices, there are no derivative of the parameters. On the other hand, I can write it, but the omega is not a tensor. It has in the transformation, it has a derivative of this local parameter. Okay.
So do we believe that it doesn't act on the spinning?
No. It's with respect to this vector field. So it's act only, yeah. It's
only
yeah. It's a flow through the manifold, not in the tangent space. So yeah, I will talk it now. Okay, I skip something. So also from the algebra structure, we just don't have transformations, but we also have a field strength, which is Poincaré algebra valued 2 form. And I think 2 also. Oh. Okay. So this is the definition of field strength, and for a definition of R's, this field strength can be written as Poincaré algebra value 2 form. So this is a component of this. It will be second function which acts on the generator in the. Okay.
You have like a bracket for the tensor.
So sorry.
So in the bracket, you have like all the field tensor. Okay, just like
Yeah.
and then you have the bracket with the
Okay.
and then on the left side.
Okay. Maybe it will be. Maybe it will be better this way. Sorry, I just used his notation, and it's just notation. And we can calculate. Say it again. Why this?
So you think that
This one depends on M. Just a notation. It's, let's say it's a P part of the F mu nu, and this is M part of the F mu nu. Okay. Okay, this one has one tangentiality too. This is just but it's just notation. It should remind you that this piece is from the P part. It's for me, it's easier to look to P here that here is one index, so it depends on P by P. But I don't get it. Okay.
The point here is that this F is a two form which is valued in the algebra. So if anything is valued in the algebra, you can expand it to the generation.
Yeah. Yeah.
It's just coefficients in the generator.
Yeah. And this is coefficient which belongs to P. This is whole. Okay, you could have in some more general case, you can have more generators with the same index structures in different levels. Let's say in non-relativistic expansion, you have let's say C0 level, C1 level, and so on, and they have same structure, but depends on another generators. So. But here it can be cancelled out. So this field strength after calculation is this guy, and the second one is this one. So this is the guy here, and the same term like this. So the Diffeus contraction with a respected curvature will be also in the transformation of the omega of omega gauge field. So for the not just rewriting these things which will be still there, we can define a new transformation where we just left these R new parts. So the new bar transformation, new bar delta can be defined as alt delta plus defill. Here is generator. You just cancel out this R and it will be just interesting terms will be in this transformation. It is another technical part. Okay, so the important things are these two. Curvatures, and we know that this is a tensor with respect to every transformations we have or every structure. It's nice. It doesn't have a derivative of the local parameters, and in space-time index, it's one form. And this is something more complicated, but still there is no dependence of omega on E. And this dependence we get in the last step of the gauging process procedure. And the last step is imposing some constraints. Imposed so-called conventional constraint. And by imposing this constraint, we should get omega, which is dependent on E. So the main brick of the whole geometry will be just E, from which we can deduce omega back, and we will see that omega is a spin connection and E is field binds. Yeah, something like this. Action? I don't have action. There is no action. Not in this case. This is another approach. This is just going from algebra to geometry without any physics behind it. We don't need gravity here. It's just purely mathematical thing. And the but of course you can construct election by this R mu ni. You can.
Just depending on the connection along the difference that
Yeah, but you don't need it. So the constraint here is that this curvature in this case will be set to 0. In general case, this could be set to the torsion, but let it simply set it to 0. So this means that we have this equation, derivation of E is equal to plus omega E, some contraction. And from this equation, when it's 0, we can deduce the form of the omega from this. We can solve this equation. So when we solve this, okay, here is already another field bind. Here is space-time index up, so it's inverse field bind. I will give a definition of this in a moment. Where we have defined inverse field binds. Which satisfy these conditions in both type of indices. So this is a formula for a spin connection. Yes. Okay, it's follow from this, I think. So it's one is redundant. Thank you. I think so. Swap. No, because this is a free index or not contraction unity. And the second tensor, we can plug their omega, and it will be a Riemann curvature to form. So this is in the this is not a metric formulation. This is a field bind formulation of Lorentzian geometry, and I think the more known is the metric one, and we can easily go to metric one by definition of metric, which will be this thing. And when we transform this, so we act with the delta bar on it, we will found that this two form which doesn't transform with respect to local transformations. So this really will be definition of metric, and through the field bind postulate, we can define Christoffel symbols. So this is an implicit definition of Christoffel symbol, so-called field bind. Wait. And because we have a zero torsion, when we plug there this omega, we will get that lambda, sorry, not lambda, gamma are Levi-Civita connection. It should. Okay, so this is just example how the gauging procedure goes. From the algebra, we get geometry, we get connection, we get curvature. In fact, classical Riemann tensor should be something like this should be a Riemann tensor. So now we will do exactly the same, but for another type of algebra, for a non-relativistic one, and we will see what's problems there in non-relativistic case. It's possible. It's really possible. Okay, so now with Galilei algebra, the structure of algebra is the following one. Okay, there are 4 generators.
We have 10 degrees of freedom in the kinetic tensor. Okay, saying 4D, but just the
4D equal to 4, okay?
P plus 1. to also add some gauge fixing to the package, because the packets now have 16 degrees of freedom each, but there is no more symmetry of them.
Oh.
Because E mu A is not symmetric.
It's a matrix.
Yeah, that's 16. So we have to get rid of
I think you get rid of 6 by the Lorentz transformations. They are antisymmetric. So yeah, there is exactly 6 Lorentz transformations in 4D. D equal to 4. So the
Okay, so we will take that's achieved.
oh,
And so
okay, you have a freedom, I think. Multiply
yeah,
this by Lorentz transformation, but here it will be in opposite way, and they cancel each other. Yeah, they are. Yes.
yeah.
Okay, so I will make a table for it. It will be better. But maybe then. Okay, so it will be also step 1. Yeah. I'm going for it. So the H generator, it will be just time translation. Generator PA are for spatial translation. So you separate the previous PA, P capital A, to the space and time part by some algebra contraction. I don't have a prescription for the contraction, but it can be obtained. JAB are just spatial rotations. So a spatial part of the Lorentz transformation. And the main difference is GA, which is just Galilean boost. And Galilean boost is just a transformation between time to space, not opposite way. So Galilean boost gives us just this transformation, that the space transform with respect to time, but not the opposite one. So this is the I think this is the first transformation which you learn in the college. It's Galilean transformation from the mechanics. So this is just a fancy way how to write it. Okay, so in step 1, to each generator, we associate a gauge field. So to H, it will be tau. To P, it will be E mu A, omega AB, and omega A. I think not. This is you can obtain by contraction of the algebra in normal in Wigner contraction by redefinition of the generators, and I think it should not be a subalgebra. Maybe some semi-direct product of this algebra times something could give you Poincaré, but for complicity, just parameters. Okay, this is the step 1, associate a gauge field to each generator. In step 2, we calculate transformations, gauge transformations of these gauge fields. So we already first we swap. Yeah, of course, all others are 0. Yeah, so, sorry, I didn't mention it. So P to P is 0, H to H is 0, and so on. Not yet. Not yet. Okay. So yeah. Not yet. It's it should be the highlight of the of the talk. Of course, the problem is here that in non-relativity, the mass is conserved charge, so it should be something here should be a mass generator. But in Galilei algebra there isn't mass, and we will see that by gauging, this problem occur. We will see that we need mass in non-relativistic theories. And I think this is another way that the gauging is not so trivial in the non-relativistic case. You will see. So in step 2, we first swap local transformation for diffeos and translation, sorry. And swap these two deltas is the same like previous. So parameters of diffeos will be xi, the new parameters for rotations will be lambda AB, and for boosts lambda A. And exactly as previous case, we can get transformations. I will just write the interesting. this is something. This will be very important, the last one. Okay. Of course. Just the same procedure as in the Poincaré algebra, the swapping. So this means that now we have two parameters. So and so on. And we will need two field strength. So for H, and for B, this is again two some Galilei algebra values two form, and we express in generators in components. So this is H component, this is P component, and here, if we will need G component, it will have the same index structure. So now it is good to write the generators in the bracket. Okay. So let's continue as we did in Poincaré algebra case. And we want to impose a constraint that R mu A P is equal to 0. And from and from this equation equal to 0, we want to get omega mu AB and omega mu A in terms of E and tau. But now there are some problems. The first one is how many equations we have. This set of equations, so R mu is antisymmetric in mu nu, so it is d times d minus 1 over 2 independent times A, and I didn't say it, d minus 1, because we have one time and d minus 1 spatial. I can say it. Components, and this is just spatial index. But we want to get this and this many spin connections, let's say. So for omega mu AB, we have, this is D for space-time index, and A and B are antisymmetric in these two indices, and it should be D minus 1, D minus 2 over 2 independent. And for the second one, we have D times D minus 1. So we can add up them, and we get D squared, D minus 1 over 2 unknown components, and we have just this portion of the constraints. Which one is bigger? This one is bigger, and we will be missing d minus 1 over 2, d minus 1, and we will be missing that much constraints. So something is missing here. So we should be more clever, more smart, because if we have just this constraint, we can't get the expression for spin connections in terms of tau and E. There are too little constraints. And this is the first hint that something is missing. And what is missing is exactly what Klaus said, that there is another generator for which we need a gauge field. But we will proceed further, and we will try to to find what is missing. The second problem with this yes. Yes. Okay. We have three more curvatures. Curvature for H. From the point of Poincaré case. There were curvature for P, where was torsion. In this case, it's the same. So the curvature for H is torsion. So we can set R mu H to 0. This effectively means the torsion is 0. So it doesn't give anything because it's torsion. But setting Rg or Rj to 0 is effectively you will have the trivial geometry, because curvatures Riemann tensors will be 0 by U. So you can make solution, but it will be trivial one, which isn't exciting. So we can do it, but it doesn't give any new thing. And second problem is that this constraint with respect, when we transform it with respect to Galilean boost, just Galilean boost, this constraint is not invariant with respect to this transformation. And as a consequence of this non-invariance, we can proceed further, but we can't expect that the solution for this two-spin connection from this equation will have the right transformation relation. So we can, but because of this, it will not be same. So we should have do a little more work. So for now, we just set this tensor to 0, which is like in Poincaré case, that the torsion is 0. But you can do this. You can work with this. It's non-trivial, but you ended up with another type of geometry. Now the final result will be Newton-Cartan geometry. But if you not set this to 0, you will end up with torsional Newton-Cartan geometry. So this is another simplification for us, but it's doable. You can't do this.
So you're saying that because we hold the torsion relations, but it's taken by that transform into the time and since that's 0, then you have to.
Yeah. Oh, it's not too much. It's not too much. It's just
well, but then it's not.
It will be useful. Usual Newton-Cartan now.
Okay, so you really put that into
the problem is you do not impose this. You can work with this, do something more fancy, and you ended up with another type of geometry.
But it seems like because you have imposed the constraint and your solution in way to stay higher.
I see. Yeah. So here should be another type of torsion.
Yeah,
Yeah. You are. Yeah. You are right. So we impose this constraint, and from this we need to have this constraint also. And no, in Newton-Cartan, you should impose this condition as well. But okay, we are not in trouble. We do not do this. We can set this to a torsion, and we get another type of geometry. Yeah. Yeah. That's another, it's torsional full Newton-Cartan, let's say. So, okay. So if we impose this, we also impose this as a consequence. Okay, but still, we can't totally fix this two-spin connection just with E and tau. So, but let's try it anyway. Let's try to solve the these two constraints equal to 0. Let's try it. This gives us nothing new because there is no omega in the first. So for the solving, we will need inverse Filbine again. What do we have? We have these two objects, and there can't be invertible because it's not a square matrix. But we can make something like projective inverseness to introduce these objects, and together they satisfy this completion relation. Okay, so they are perpendicular in each position of the space-time indices. They are normalized. Better, they are normalized. And together they make full rank space. Okay, so we try to solve this. The solution can be written in, let's say, this parameterization. Where y is something new or something which is defined by an omega mu a. X. Okay, we have two new guys, X and Y. X is this contraction of omega A, and Y is this contraction of omega A. So this is a parameterization of a solution because we don't have enough constraints. Yeah. This is defined with respect to same one. It's because we don't have enough constraints. Now, what we want. Yeah. Mm-hmm. You try to solve system of equations, and you should have some parameters there. Yes. Yes. Okay. I understand it like this. You have something equals to 0, and you try to solve it. So you in RP, where is RP? RPs. RP is this thing, so it's equal to 0, and you want to get this guy and this guy out of it. So first you times it by tau. When you time it by tau, this cancels out. This is what you get, but this is not cancels out completely because there is anti-symmetrization. So you try to rewrite it as you have omega on the one side and the rest on the other side, and the only how you can dictate it by self. So you make some recursion there. This is how I understand it. And this guy is okay because this guy you can parameterize by this, but this you should parameterize by itself. It's okay. Try to solve this. I think you will see it. Yeah, tau and E. You have two projections. Let's say this and this. The first cancel this, so you will have some omega mu A alone, but also because of anti-symmetrization, the second one survives, and you can use the second equation to plug it in first and do some more steps, and the best what you get is this. It's really complicated. I don't know. For Poincaré case, it's complicated. For this is more complicated, really. Oh. Really? Mm-hmm. It's possible. I really don't know. We will see that these two new geometry things depends on the new gauge field then. So we need to see omega A, omega AB. But without nu, what is this object? Oh, okay. It's right. But this one will not be zero. And this could be
And this is a different one.
In one upstairs, just the Lorentzian information plus line.
yes.
And from that, we also know the relation between that object and the structure.
No, we don't have Christopher symbols yet. The problem is now we have two spin connections, not just one. So how do we want to get right Christopher symbol? You will have some, let's say, projection to the time of a Christopher symbol and projection to the space of the Christopher symbol. But we will see that, in fact, these two new geometric fields depend on the new gauge field, which corresponds to the mass generator. Okay, or some generator which will be in the bracket between G and P. So it will be a mass generator. Okay. So we have a transformation, gauge transformations from the algebra. What should transformation of omega mu AB and omega mu A look like? We get it in step 2. And from these transformations, we can get gauge transformations of these new two geometric objects, Y and X. And we will be interested just with the transformations with respect to Galilean boosts. And if the solution of the constraints have the right transformation relations, then the transformations of Y and X should be this. Okay, here we can end and we can say that, okay, the geometry what we get is this with two new geometric fields which transform this way, and we have two spin connections and so on. But here we can notice that we do not need two new fields, but it will be enough to have just one field. Call it M, which transform in this way with respect to Galilean boosts. And if we, with this M field, we can construct this two new fields. Okay, so I want to say that it's sufficient to have just one new field in the solution, not two. And you mean this? The condition was that we want the no, the curve. We want the gauge transformations from the algebra. So we have in step 2 we have this prescription, and we want that this is something, and when we transform this guys, we want the right transformation of these new fields to get this one. This was the condition. And in fact, why? Okay. We have d minus 1 over 2 unknown things. And the thing here is that there is no expression which has the field M itself. It's always is in this form. It's always in the unsymmetric derivation, which gives us exactly so many unknown. So the field was something hidden there. There were no direct, I don't know how to say it. There were no M field, but just the curl, just the derivation of the field was hidden there. This is why we don't see it before. So this is a complete geometry what we get. So in this geometry we have three fields. We have two spin connections. And we can again introduce metrics. Now, not just one matrix, but two generate metrics. It could be done. It could be shown that these two guys are have the right transformation properties of metrics. They are two forms or two vectors with respect to diffeomorphisms, and they don't transform in inner transformations. And from this we can get Newton-Cartan geometry. But the main question should be, what is this M mu? Why is there the M mu? We get this M mu by some quite difficult procedure. It was quite not so natural, not so clear way how to get this. The tau mu. There were no error. So it could be say that we add this M by hand. It's something which we should add there to get a right non-relativistic geometry. So we can ask ourselves, is there a natural way how to implement the M into the geometry or into the algebra itself? Can we add the M to the algebra as new generator, which gauge field will be M mu? So can we add new generator to algebra? So it's, and the question is, can we, and then how? So we have Galilean algebra plus some m. And now how we can add this m to the algebra? The crucial is that it can't be a direct sum of two algebras because of this transformation relation, because these transformation relations give us some non-zero commutator between generator for m nu and generator for e mu c. So from this, we can see that there should be this should be equal. Okay, lambda c goes for G, E goes for P, and this goes for M. And there is no other all others transformations are trivial. So this is the full transformation will be this plus the derivative. So this will be the only change. So all others commutators will be 0. So and M commutes with all of each others. So from this hint, we can make guess that it will be a central extension of the Galilean algebra with a new bracket. With this one. And this algebra with H, M, P, A, B, G, H is called Bergman. Algebra. And again, we can make gauging of this algebra, and we get exactly the equations and the geometry which we get. So and now physics, why M is important. It's exactly as Klaus said, because we have two conservation law. We have conservation law for energy and for mass in non-relativistic physics. And this is net current with which corresponds to the conservation of mass. So we need this in the non-relativistic theory, unless we dealing with the zero mass quantities, but in non-relativistic physics, when there is no mass, there is no dynamics, so it doesn't make sense. So really, when we gauge Galilei algebra, we found something strange, and this means that there is something missing, and the missing part was the physics behind it. So maybe if you want to know what happens here, look on the video for the Jan Rosseel. It will be much better than my presentation. Also, the slides are much better. And I think, really, I don't think so. But for me, this was, let's say, new way how to understand a Bergman algebra. Not some just, oh, we start Bergman algebra and we get Newton-Cartan geometry. This was, for me, it was more natural to try first Galilean algebra to get geometry, and something is missing. Wow, what's missing? Then just as every paper in Newton-Cartan geometry starts, let's say we have Bergman algebra and try to calculate something. For me, it was very nice lecture. So if you are interested, look on the videos. There are a lot of another stuffs about non-relativity. For example, there were a lecture about non-relativistic strings, which I think a lot of you would be very useful and interesting. So thank you. And if you have any questions, please ask. I hope I can answer it.
So everybody else after seeing this, so if we start the part,
You get exactly Newton-Cartan geometry with everything. No, it will be easy. Yeah, like in Poincaré case, everything will match. Yeah. And in fact, all this gauging has roots in gauging of algebra in supergravity. So you can gauge any, let's say, algebra, not just, or superalgebra, not just these two or these three. From every algebra you can get geometry, and in my field it's quite interesting because non-relativistic geometry are still not very well understood. So it's a nice question or opposite questions. I have a non-relativistic geometry. What's a non-relativistic algebra behind this geometry? I think it's a quite non-trivial question for this field.
I just one more comment one, but then it's more like a philosophical point of view. So I was a bit, I'm a bit more in the, I mean, agree with starting the back. That's because even before we gauge, then I think it's more like a historic accident that we have identified the name and the graph that we have. And I think because people view it from the ground, they write down the Galilei information. They're not worried about what are the generators. They're not having the human perspective. That just came later, and people have just introduced these generators, momentum boost in a way, and nothing to be about it. But if you start to write down the most natural representations, say for a free particle, non-resistant particle, then you realize that your generators, you boost and your momentum do not commute, and then move them out. So it's the most natural. I think the Wagner algebra, I don't know why it should be invented in the 50s by Wagner, because I think it's really the most natural thing, and it should be but anyway, that is what it is.
Okay, this is something like to get Bergman algebra without any physics. just purely from mathematics. But when you do physics, it's because of conserved charge, it's quite obvious that this is the right one.
So if you these two parts of the theory, you start with the algebra, some generators, some commutator, and in the end you get some geometry. Let's say it'll just become some logarithmic. So is there always one correspondence between each other, or is there more algebra like the same geometry?
There, of course, more algebra ending in the same geometry, but just by some redefinition of the generators, you can get a same geometry. But I think there should be also a case that you get nothing, like your geometry will be much more constrained, that it will be just, let's say, everything flat. So it's a cherry pick, I would say.
It's interesting to do it the other way.
Yeah, yeah.
But that must be a much more difficult problem. Maybe you get some algebra. This may be some known algebra, but you would not know. You wouldn't find some definitions of fields.
I do it this. I have some geometry, and I try to find algebra that have the right transformation relations. So I have some, let's say, non-relativistic algebra, and I do more contractions. And finally, I found the contractions that make sense, and I get the right transformations. And okay, and I say this is the algebra for my geometry. I don't know the opposite way, like implication just.
Also, this the end of your control is
Mm-hmm.
like a unique way of how to fix this problem, because you just combine these two fields, I and X, and you say if I have this M, then everything is simple, but
You can
some other field.
You can end here. Let's say you don't have an M field. You could have two new fields, and it will maybe it will end in another algebra. Okay. This is not Gauge field, so I'm saying nonsenses. So, but okay, you can end here and say this is my final geometry. I will deal with it.
That would be in some sense similar to the pattern that we would be against.
Yes. I think. I'm not sure, but I think.
Was there? But that mass and graph, that will be referred to what?
It's referred to what? Okay. This is a net charge for mass symmetry. It's strange, but
That's our global symmetry. Comes from the global symmetry.
Yeah.
All right. Because I wonder, I know it's not just maybe there could be some connection between that and the result of the APM action, the latest below.
no.
Okay. Using the asymptotic case, the action is exactly the mass contained in the region. So there is this symmetry in this conserved quantity in time, like that. But so this we are saying, if y is 0, you don't have that time.
Yes. okay, maybe other way. If m is 0, then you don't have y. But talking about this is non-relativistic physics. And if you have no mass in non-relativistic physics, you don't have any motion. Due to second Newton law, you need a mass. So it doesn't make sense in non-relativistic physics to don't have a mass. Okay, any more questions? I think we can end and then discuss by Blackboard if they're interesting. So thank you for attention, and I think in 2 weeks, Ari will have a talk about summer school, the same as Standa was attended. Okay, so bye.